Welcome everybody to the latest edition of the Physics Corner, a series of videos in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today, we're going to take a look at a baseball player sliding into second base. We're not going to tell whether the player is successful at stealing the bag or not. What we are interested in is the coefficient of friction between the ball player and the ground while that's happening. This is a decently sophisticated problem, so we're going to take our time with this. This involves the intersection of force and energy methods, if you will, and is worth a detailed look. As usual, I'm going to solve for the algebra of the problem, and then we'll use some sample numbers to plug in to see what a realistic solution would look like. So let's get started. So here's the situation. Our baseball player is attempting to steal second base, and at the moment the ball player starts to slide, the ball player is traveling at 6 meters per second. Now, to keep this sort of in accordance with more realistic expectations, we could set the speed of the ball player to 0 when the ball player reaches second base, but this is usually not how it actually runs. If you watch an actual ball game, the player usually is sliding with some speed when the ball player reaches second base. So let's include that. Let's actually have a speed for the ball player, and in this example, we'll set it to 2 meters per second. So the ball player starts the slide at 6 meters per second and reaches second base at 2 meters per second. Now, we'll also assume that the ball player slides for 4 meters, and that is the information we're given. We'll also, as usual, assume that gravity is equal to 10 meters per second squared if we need it, as we usually do in order to round off the numbers so it's easier to do the calculations. But as always, to remind you that if you're doing an actual lab problem or more sophisticated calculation, you should use the 9.81 meters per second squared number. All right, so in this case, rather than having me write down the knowns and unknowns to start with, I thought it'd be a little bit more instructive to go through this carefully to pick out what we know and don't know. Because there is a lot that we know, there's even a lot more that we don't know, but some of what we don't know will not necessarily be useful or even needed to solve the problem. And so this is going to be one of those situations where we can sort of pick out what we need and ignore some other items. And let me show you what I mean. So let's do the knowns first. Those are the things that are written. We already said this, that the acceleration due to gravity will be rounded off to 10 meters per second squared, like that. Let's also take a look at the speeds. Those are numbers that are given to us. So the original or initial speed is 6 meters per second. By the way, in case it's not obvious, let's assume that going forward is positive for our runner in all situations. That does matter, by the way, as we'll find out. Okay, the final speed of the ball player will be 2 meters per second, like that. And the distance the ball player slides, which is what we're interested in, is 4 meters. Okay, notice what we don't have. Among other things, of course, we're asking about the coefficient of friction. Specifically, we're asking about the coefficient of kinetic friction, or as is sometimes called, the coefficient of, surprise, surprise, sliding friction, right? So that's just a coincidence. In any case, we don't know that, but there are also several other items we don't know. We are not given the mass of the ball player. We are not given the acceleration of the ball player. We're not given the force of friction acting on the ball player, so whatever that might be. We are not given the normal force on the ball player. And because this problem also involves velocities or speed specifically, you might wonder, what are the energies acting on the ball player? Well, since the ball player is on a level surface, there's no need to worry about potential energy due to gravity, and there's no springs involved, so there's nothing like that to worry about. But there is kinetic energy, right? So we don't know what the original kinetic energy is, we don't know what the final kinetic energy is, and therefore we don't know what the change of kinetic energy is, or if you prefer talking about this way, we don't know what the work done to the ball player is during the slide. So this looks a little bit daunting when we write it this way. Okay. Now, because this is a combination problem of force and energy, if you will, because we're asking about something that definitely involves forces, the coefficient of friction business, but also information that's given to us in terms of speeds, which sounds like energy ideas, we're going to need to sort of mix and match. And that's what makes this a little more difficult or well-rounded problem. So, because there's forces involved, even though it's an energy problem in a sense ultimately, we still want to draw our familiar free body diagram. So let's do exactly that. So here's our ball player, and the ball player's going to be going forward. So for our purposes, let's assume going forward in the positive x direction is like that. And for convenience, we'll have positive y going up that way, as we usually do. And then what are the forces acting on our ball player? Now, as always, remember, free body diagrams involve only forces. They don't involve velocities or displacements or anything else. It's simply forces, right? So let's draw only forces. So there's a weight on the ball player going down. There's a normal force going up like that, of course. And because we're assuming the ball player's slide is perfectly horizontal, that will be actually pretty easy to handle. And then there's the force of friction acting on the ball player. Now, force of friction always opposes motion, right? So if the ball player is moving forward, force of friction, which I'll designate little letter f here, is going to act backwards. F sub k specifically, if you want to be careful, because it is a kinetic friction force. And that's it. There is no force driving the ball player forward. This is a common misconception, or at least something that's easy to misconstrue about such problems. Once the ball player has started the slide, there is no force acting on the ball player to keep the ball player moving. That is simply our good old friend inertia, right? The tendency of an object to keep moving in the same direction with the same speed, right? That's the first law of motion. But that's not a force. That's not what that is. And it doesn't belong in a free body diagram. So there is no force driving the ball player forward. Once the ball player, say, jumps down, if you will, to start the slide, there's no force going forward in any part of this problem. So during the slide, these are the three forces at play. All right, so forces in the y direction, if I sum those up, I'll do this first because it's the easier part to throw to conceive. We have normal force going upwards, weight going down, and because everything is perfectly horizontal in terms of the motion during the slide, there's therefore no vertical motion. If there's no vertical motion of any kind, there's no vertical acceleration, therefore no vertical force overall. So that is 0. Okay. What about the x direction? This is where it gets a little bit more interesting. In the x direction, the force is friction acting in the negative direction. So it looks like that. Okay. Is it kosher to put a negative sign on that friction and have that be the only force? Yes, it is. We decided, or I decided, earlier on that the positive direction would be going forward. If the force is acting backwards, we need a negative sign on it. And that's perfectly okay. In fact, we need to be consistent. If we decided going forward is positive, friction is going to be negative. Has to be that way. Also, because there's only one force at play, that will be equal to mass times acceleration of our ball player, ma. Again, remember, the sums of forces, if there's no other force to sum up, if there's only one force there, there's not much of a summation to do. That means, by definition, there must be a net acceleration. So you can't set that equal to 0. Last equation that we need to introduce is the relationship between friction, coefficient of friction, and normal force. And that particular equation, which is not a sums of forces equation, this is just a relationship between friction and normal, is this. Kinetic friction equals the coefficient of kinetic friction multiplied by normal, like that. That equation is vital. It's not one of these two equations where you're summing up forces, but if you don't have this equation to throw into the mix, you're not going to be able to solve the problem, because this is a friction problem. And hopefully, from the context, it's asking for the coefficient of friction here. That's a hint that we have to have that. We have to have some equation that has a coefficient in it, right? So that's one way to say it. And that's partly why I asked the question in this fashion. So to point out that the bit there. All right, so how do we get started? Okay, from the y equation, this one's pretty easy to see. Normal force must equal the weight of the ball player. So that one's easy, okay? Do we know what the weight is? Do we know what the mass is? Do we know what the normal force is? We don't have numbers for those yet. But here's something about these kinds of problems, and you have probably experienced a little bit of this so far in some of your studies, is that some of these will either be substituted away or will cancel and won't be necessary. So Let's hold off on worrying about what the value of the mass of the ball player is for the moment. And let's just assume that that will take care of itself. And you'll find out that, yes, that will be the case in this problem. Okay. All right, here's the other problem. Friction equals mass times acceleration. That's already written as such, so we don't need to mess with it. But friction is also equal to coefficient multiplied by normal. So let's play with that a little bit. So friction equals coefficient times normal. But we just said normal is the same as weight. So let's substitute. So friction coefficient multiplied by mg gives us our friction force. Something else to always remind everybody of: force of friction, coefficient of friction. Two separate things, right? That's something else that's easy to get mixed up, especially, say, in a test situation where you're pressed for time, to get the coefficient and the force themselves kind of traded back and forth. Well, they're not the same thing. They're related, but they're not identical. So, all right. Now, what can we do with all this? Well, let's take a look at our friction equation here. Friction also, though, equals a negative ma, like that, right? Okay. So here's something that kind of announces itself. If you look at these two equations here, this must be the same as that, right? So UKMG must equal a negative MA, or if you like, UK must equal a, check it out, a over G. And there's a negative sign in there as well. Now, coefficients aren't negative, right? Coefficients have only positive values. Let's see if that plays itself out too. So this is kind of a side comment, if you will. This is where we're heading. If we can somehow figure out the acceleration, we can, and we already know what gravity is, we can solve for the coefficient. So there's a couple of ways to go about this, all right? I'm going to show you a couple of different methods for doing this that are related to each other, but let me show you. So let's go ahead and take a look. All right, so keeping in mind, this is our result so far. If we can find acceleration, we can find, we already have gravity, we can find the coefficient. Is there a way to solve for acceleration given the information we already have? One way to do that is by old-fashioned equations of motion. So this particular way of doing things is a callback to some physics that you did very early on in the class. One of the equations looked like this. The final velocity, or speed squared, equals the original speed squared plus 2 times acceleration times change of displacement, like that. Okay, let's run this through and see what happens. So we solve for acceleration. That means, and I'll speed it up a little bit here, that acceleration will ultimately equal Vf squared minus V naught squared, and then divided by 2 delta x, like that. Okay. Now, that's an algebra solution. We have the numbers to put in there. If we do this, we'll get our answer. Well, let's go ahead and try it. Let's see what happens. So, Vf was, now remember, you gotta be careful about this, right? Vf was not 6, but 2. Remember that the ball player was slowing down, and the final speed is 2. It's easy, again, to get caught up in thinking you have to do bigger minus smaller, because that's how you sort of grew up with numbers. But that's not the case. We can always have the smaller number subtracting the bigger one. That's possible. And in fact, that's what we're doing here. So it's not 6, but 2 meters per second, quantity squared, like that goes in here. The original speed was the 6. And so it looks like that so far. Then 2 and the delta x, which we said before was 4 meters, like this. All right. So 2 times 2 is 4. 6 times 6 is 36. 4 minus 36 is a negative 32. We have 2 times 4, which is 8, like that. And, of course, the units will work out carefully if you watched them. And negative 32 divided by 8. The acceleration is a negative 4 meters per second squared. All right. Now we can do our final calculation. Coefficient is negative a over g. And now this is why we kept the negative sign earlier, right? Because if we hadn't, we'd be calculating a negative number for our coefficient. But notice what happens. Negative of a negative 4 meters per second squared divided by 10 meters per second squared. Negative times negative cancels. 4 divided by 10 is 0.4. And our final answer for the coefficient is 0.4. And that's it. Remember also, by the way, that coefficients don't have any units. They're just a ratio of forces, therefore no units. Again, a difference between coefficient versus actual force of friction. Notice here, at no point do we have to consult the amount of mass or the actual amount of force. I mean, we did use force equations, but we didn't have to do any of that. Okay. Now, in case you're wondering, or here's another way to talk about this, let's use energy, specifically conservation of energy, to solve this problem. And what would that look like? It's a little bit more sophisticated, but it also gives a little more insight as to what's happening physically. Now, by the way, if we do this correctly, hopefully we will, we should get the same answer as we did here, right? Because the physics hasn't changed, the numbers haven't changed, the situation hasn't changed. So no matter how we go about calculating this answer, whatever method we use, if the methods are correct and our calculations are correct, we should come up with the same answer, right? So hopefully, we'll see, we should have an answer of 0.4 for our coefficient. All right, so let's try it. So energy methods says this: the energy going in equals the energy coming out of a situation, all right? Or the original energy equals the final energy, so on and so forth. All right, what kinds of energy do we have? All right, well, a couple of ways to go about this, but let's go this in detail. So at the beginning, the ball player has kinetic energy. So original kinetic energy like that. Again, there's no potential energy of a spring to worry about because there's no spring. There's no potential energy from gravity to worry about because the ball player, while sliding, is at the same height. And so there's never a difference in vertical distance. Therefore, there's no gravity potential at play. So the only thing that's happening here is kinetic energy going in. All right. What happens coming out? Well, the ball player has some kinetic energy at the end of the problem, right? But what else is going on? This is where it gets a little bit trickier, and you have to remember what is going on for energy. So far, there's a big tendency for students to think, okay, once we learn what these energies are, there's kinetic energies, there's potential energies, and there's a very simple idea that you might forget, that the original definition of work was a force times a distance. In order to get to kinetic energy and potential energy, you had to go through this rigmarole and derivations and whatnot, but that's still true. Work is still at play. And so what kind of work do we have? We have work done by friction. Okay, now how's that going to look? Let's work this out. So, kinetic energy, 1/2 mv naught squared for the original kinetic energy, a 1/2 mvf squared for the final kinetic energy, and then what's work? Work is ultimately force times distance. So work is a force times a distance like this, right? Okay. So let's write that in. Force of friction multiplied by distance. I'll use the little letter f now because that's the specific kind of force we're talking about. All right, so here's the cheat, if you will. Let's keep writing the kinetic energies for the moment. But what's the force of friction? Earlier we determined, bring back our previous page so we can see it. Earlier we determined that friction is equal to coefficient times weight, mg. So let's substitute. So it's coefficient mg and then a delta x like that. All right. Now, by the way, why is this work a positive number over here at the moment? That's because this is energy that is done by friction. The friction has gained the energy, if you will. So we're going to leave it that way. Let's see if it works. All right, so we're interested in solving for coefficients. So let's do that. Take a look carefully at the formula here. A couple things that show up. One is that the mass is common to everybody. So mass is here, here, and here. And therefore, we can cancel mass. We don't have to carry it. And I'll have a 1/2 V naught squared here equals a 1/2 Vf squared here plus a mu g delta x like this. All right. Let's subtract this from the other side. So I have a 1/2 V naught squared minus Vf squared in this case. All right. And then we have equal to mu g delta x like that. Okay. We're solving for mu. So mu equals V naught squared minus Vf squared here. This 1/2, I'll just take this 2 and put it down below. And we're dividing both sides by g and delta x. Looks like that. All right, V naught was 6. Vf is 2. Like that. Then we have a 2 times 10. And delta x, if you remember, was 4. Okay, if we look carefully, we have meters squared per second squared on top with meters squared per second squared at the bottom, so there will be no units, so that's good. How about numbers? 6 squared is 36 minus 2 squared, which is 4. 36 minus 4 is 32. So 32 on top there. 2 times 10 times 4. 2 times 10 is 20. Times 4 is 80, like that. And if you look very carefully, this, if we notice that all these terms have a common denominator of 8. 32 divided by 8 is 4. 80 divided by 8 is 10. Yeah, and lo and behold, same answer. Okay. So there's 2 different methods for doing the same problem. One is by using old-fashioned equations of motion. In other words, physics being one of those topics that builds on itself. Just because you learned equations of motion back in chapter, say, 2 or 3, doesn't mean you should get rid of it. Keep it. It's still useful. Or you could use this newer method of energy and come up with exactly the same result. Now, this is a little bit more complicated, you'll notice, right? The solution was a little bit more involved, but it's also a little bit more insightful, and then it tells you what's happening and why. It tells you that the ball player had an initial kinetic energy. When the ball player reaches second base, there's a little bit of leftover kinetic energy, but most of the remaining kinetic energy was turned into work that was done by friction. That work went into friction. And same result. So, 2 different methods for solving the same problem. Again, this is a more sophisticated problem, but it gives you a good idea. So, here's something else to comment on before we leave off for the day. These kinds of problems with friction like this are very common. You'll often see this where you have an object that slides and you want to calculate the speed of the object at the end, or its acceleration, or in this case, the coefficient of friction. And they're all can be approached in these 2 different fashions. And so all of them work in this way. I always suggest find a method that works for you, that you're really good at understanding, that you can be comfortable with, and tend to go with that one, especially, say, in a test situation, because there you're always pressed for time, right? But in either case, you can see that either method works just fine. All right. Okay, everybody. Technical support for this program is supplied by Cindy Geltrow and Sophia Turner. Funding comes from the University of Mississippi and the University of Southern Mississippi. We filmed this in Hattiesburg, Mississippi. I am your host, Dr. Christopher Sorolla. Thank you for your attention, everybody, and clear skies.